Welcome. So this is lecture 27 of Introduction to Order Theory. We are starting a new chapter, chapter 9. It's about Greene-Kleitman theory. So Greene-Kleitman theory is a theory which is a very strong extension of Dilworth's theorem. So Dilworth's theorem says, and it's dual, they say that a comparability graph and the co-comparability graph are perfect. And here we will see a much stronger property. So we are going to start with an introduction, which is basically a statement of the results. And so in the whole lecture today, we are going to assume that we have given partial order and it has n elements. So these are things we are going to refer to from time to time. And now here is a crucial definition. A family of chains is a set of disjoint chains in P. So in this lecture, family of chains, always the chains are disjoint. And now when we have C, a family of chains, then we denote with cardinality of C. This is the number of chains. And then we have a second symbol. If we take this, the norm, say, and this is nothing but the cardinality of the union of the chains. So this is a number of elements covered by the family. And here's a shortcut notation. This object, the union of the elements covered by chains in G, in C, this will also be written as union of C. And now if we have a family of K chains, then we also speak of a K chain. And of course, the same terminology can be applied to antichain families. So, family of antichains is a set of disjoint antichains in P, and typically we use the symbol A, a family of antichains. Then we have, this is the number of antichains in A, and the same thing here. This is the number of elements covered, and we speak of the union of A as the set of elements covered. And typically, instead of taking a K here, we take an L. So we speak of L antichains. Okay, and now with this terminology, we can already state the first two theorems. So theorem 1 in this theory here is at the maximum of A, where A is an L antichain, equals the minimum over, here we go over chain partition, and then we sum over all chains in the chain partition, and we weight each chain with the minimum of its size and this parameter L. And yeah, so the theorem is that this holds for every reasonable L, which means that L is between 1 and the height of P. We have this identity. The maximum number of elements that can be covered by an L antichain equals the minimum of this weighted sum over the chains in a chain partition. And yeah, here are remarks. Well, the first remark is that if we take L equals 1, then we will talk about one antichain. So this is just a single antichain, and the left-hand side is the width. And on the right-hand side, we work with L equals 1. So the minimum of the size of the chain and 1 is always 1. So we just count the number of chains. So it's equal to the minimum of the number of chains in a chain partition, and this is inverse 0. And the second remark is that actually, if we think of this equation as two inequalities, one of the two inequalities is kind of trivial. So for every pair A, C, A and L antichain, and C chain partition, we can write the following. We can look at the size, the number of elements covered by A. Well, and this is equal to the number of elements covered by L intersect the union of the C, since this is all the elements. And now, since the chains here are disjoint, we can break this into pieces. This is the sum of A intersect C, C going over the chain partitions. And now, if you look at this, then you have two obvious bounds on this contribution. One bound comes from the size of the chain. It cannot intersect the set in more than the size of the chain. And the other comes from the fact that this is an L antichain, so it can intersect C in at most L elements. So this is at most the sum of the minima of C and L, where the C is still over all chains in the chain partition. So this holds for every pair, and if we find a pair with equality, we are obviously okay. So this is these two remarks, and now here is theorem 2. And theorem 2 is just the dual of the theorem. You exchange antichains and chains, L and K, and height and width. So for every K between 1 and the width of P, the maximum of the number of elements covered by a K-chain is equal to the minimum, where the minimum is taken over all anti-chain partitions, and we weight every anti-chain in this anti-chain partition by the minimum of the size of this anti-chain in K. And yeah, of course, this is a generalization of the dual of Dilbert's theorem. So for K equals 1, this is just the dual of Dilbert's theorem. And again, this inequality here is easy. Okay, so these are the first two theorems. We are going to have 5 theorems in this series. Theorems 3 and 4 depend on yet another definition. So definition: a chain partition is L saturated if it gives equality in theorem 1. And of course, we again have the dual definition. Anti-chain partition is K-saturated if it gives equality in theorem 2. And yeah, so here with these definitions, we can state the next two theorems. Theorem 3, this is called the T phenomenon for chain partitions. And what is it? What does it say? It says that for every L which is reasonable, between 1 and actually strictly less than the height of P, there exists a chain partition C, which is simultaneously L saturated and L plus 1 saturated. And yeah, you may ask yourself, what does the T mean? The T means T is a shortcut for transition. So you can always go from one instance of the theorem to the next if you have picked the right chain partition. Yeah, and again, theorem 4 is just the dual one, the transition phenomenon for anti-chain partitions, and yes, the statement is 1 less equal k less than the width of P, then exists an anti-chain partition which is k and k plus 1 saturated. Good. So this is the first 4 theorems. Then finally number 5, theorem 5. It says that the values that you obtain, if you denote the maximum size of a K chain as the K's height of the poset, and the maximum size of an L antichain as the L's width of the poset, and all these parameters, width 1 up to width h, and height 1 up to height width, height w, all these can be encoded nicely. So here is how this goes. There exists a partition lambda of n. Let's do it explicitly. Lambda of p, such that WL equals the maximum of the number of elements covered by an L antichain equals the number of squares in the first, let's be more precise, in the longest L rows of the Ferris diagram of lambda of p. And the dual, of course. The K's height, meaning the maximum of the number of elements covered by a K chain, equals the number of squares in the longest K columns of the very same object, the Ferris diagram of lambda. Okay, so these are the 5 theorems which give this strong extension of Hilbert's theorem, the strong extension of the perfectness of comparability and incomparability graphs. Maybe it's a good idea to look for an example. So here is a P we are going to work with. We have a chain of length 5, and then something deviates from here and something from here. And now let's see, what can we say? Looking at these 4 elements, we see that the width is 4, and from the drawing we see that the width is at least 4, and from the drawing we see that there is a corresponding chain partition, so the one width is 4. the two widths, I claim this is equal to 6. And the way I'm going to prove it is we look at this very natural chain partition. And now if we look at these elements and these elements, these are 6, and if you look at the right-hand side contribution of this chain partition, this is also 6. So we see that W2 is equal to 6, and W3 is equal to 7. And for this, I take a new drawing of this poset, and now we are going to look at what's wrong with my oops, this is my poset. Still the yeah. Still the first two things are true, and now looking at this chain partition, we immediately see that W3 is equal to 7, W4 is equal to 8, and W5 is equal to 9. And this green chain partition is 1 and 2 saturated, and the blue chain partition is 2, 3, 4, and 5 saturated. And from these data, we know that this Ferris diagram of lambda looks like this. So the first row is of size 4. The two first rows together are of size 6. And then we have first column, which is of size 5. And yeah, now this Ferris diagram is telling us immediately that H1 is equal to 5, H2 is equal to 7, H3 is equal to 8, and H4 is equal to 9. And yeah, of course, it's a very easy exercise to get these values directly from the poset. Okay, now let's talk about the proof. The proof of all 5 theorems will be a consequence of analyzing the run of a special min-cost flow algorithm on a special network, which is, of course, related to P. And yeah, this is a beautiful proof due to Andras Frank. And the proof is based on yet another concept, which is closely related to K-chains and LN chains. We are going to talk about orthogonal pairs. So here is the definition. C and A is an orthogonal pair if, well, C is a chain family, A is an anti-chain family, and now in addition, we need two properties. The first property is that together the elements covered by the chain family and the anti-chain family is everything. So the ground set of P is equal to the union of what is covered by the chain family and what is covered by the anti-chain family. So this is property 1, and property 2 is that for every anti-chain in this family and every chain in the chain family, we have at the intersection of the two is equal to 1. So this is where this terminology, this orthogonality comes from. Yeah, so this is the definition, and now here is an observation. If we have that, if we have an orthogonal pair, and yeah, if C is a K-chain and A is an anti-chain, then the claim is that C, the number of elements covered by C is equal to HK, and the number of elements covered by A is equal to WL. And to see this, we let C plus and A plus be obtained by adding singletons to C and A respectively to make them partitions. So we add every element which is not covered by C to C as a single element chain. And now, let's have a look at the following sequence. So when we want to see how many of the elements covered, the number of elements covered by C, and this can be obtained by summing over all chains in the chain family and over all anti-chains in the augmented, it should be a plus, in the chain partition obtained from A, the anti-chain partition obtained from A, and just taking the intersection of C and A. Fairly easy. So we go over all elements in A plus, and now if this is a singleton, then this singleton is covered by some chain because of property 1. And we can clearly write this is the minimum of size of A and number of chains in C. And if this A is an anti-chain which belongs to the family A, then it is intersecting every chain in C, so we get this contribution. So if this is equal to K, then we have a K chain family where the number of elements covered is equal to the contribution of this anti-chain partition, where here we have a K. And this proves that these are both optimal. In particular, the C is a K chain of this size, and the A plus is a K saturated. Let's put it here. A plus is K saturated, and by the very same computation, we see that C plus is L saturated. Good. Now we have all the definitions that we need, and now we are going to study the network and the network flow, which are going to give us the result. So let me clean the board. Okay, so we are ready for 9.2 network flow. So just to say what we are going to do, the network will give orthogonal pairs in the sense that we just discussed, and this will show that we have this saturated chain and anti-chain partition that we need, and we have the corresponding dual K and L chains. Okay, so which prove theorems 1 to 5, actually. Okay, so the network. The network N of P is, well, it has a set of vertices, a set of edges. The set of vertices is equal to x prime, x double prime, and then we have two additional points, vertices S and T. And let me indicate this. So we have S, we have x prime, x double prime, and T, and here we are going to produce this network for an example poset, which is just A, B, C, D. So we have A prime, B prime, C prime, D prime, A double prime, B double prime, C double prime, and D double prime. And now let's see what are the edges. The edges are, first we have all the edges of the form x prime, y double prime with x less than y in P. So this is an object that we already know. These are the edges of the split. So we have the edge, these edges are in the network. And then this comes together, and we have three edges related to every element x in P. We have the edge S, x prime, we have x prime, x double prime, and we have x double prime T. And this is for every x in the ground set. So let me add them. So we have these verticals. This is, and I'm going to add the other edges in white again. This is the network of this poset. And yeah, then we have additional data. We have capacities, and we have costs. And the capacity is rather trivial. We have the capacity of every edge is 1. But this is a directed capacity, so we can send flow from C prime to C double prime, but we cannot send flow in the converse direction. And then we have costs. And this is, we denote them by A, and the cost of an edge is 1 if and only if x, y is equal to C prime, C double prime for some C, and it's 0 otherwise. So my colors already encode the cost. The cost of the yellow edges is 1. Okay. Now, what can we say about flows in this network? We observe that the maximum flow on n has flow value equals to n. So if we sum the capacities of all edges leaving S, then this is n. And we can only send a unit there. And actually we can reach this value by just taking the flow in this paths, S, x prime, x double prime, t, for each x. Okay, so this is the maximum flow. And now the goal is that for every value less equal n, find a min cost flow of value v. And yeah, to see that we really work with min cost flows, we need some optimality criteria, and this is important thing, proposition. Optimality criteria. If we have a flow of value v, and if we can find some function pi from the vertex set of n into the non-negative integers with the property that the pi on the vertex S is equal to 0, and two additional conditions. So if we have an edge where the potential difference is less than the cost of this edge, then on this edge we have flow equals 0. And if we have an edge where we have that this potential difference is larger than the cost, then the flow on this in this edge is saturating the capacity. Yeah, so if such a pi exists which has which satisfies these conditions, then we know F is a min cost flow of value v. Yeah, this is important. This is something we are going to use throughout the proof of our theorem. So let's do the proof of this these optimality criteria. So we define Rxy to be Axy plus pi of x minus pi of y. So this is some function on the edges which depends on this potential but not on the flow. And now we take f a flow and we consider the cost of f. And this is equal to the sum of the flow values on the edges times the cost. And now we can replace these A's by this here, by the R's. So this is equal to the sum of fxy rxy plus the sum, and now because we replace the a xy, we bring the stuff on the other side, pi of y minus pi of x fxy. Now let's study this here. We are going over all edges. In particular, if we fix a vertex z of our network, then we get all the in edges with a contribution of the potential of this vertex times f positive, the in edges, and the out edges with a pi of z and times the flow negative. So we get a pi weighted inflow minus pi weighted outflow. And by flow conservation, this is 0 for every vertex which is not S or T. So flow conservation contribution of Z not equal S and T is 0. And now let's look at S. By definition, pi of S is 0. So the contribution of S is also nothing. And the only thing where we get something is for the t, pi of t times f of z to t. So, and every unit of flow is ending in t. So the pi of t is multiplied by the total flow. Okay, so this right-hand side contribution is equal to pi of t times the flow. And now we have this contribution, and what we do is we split this into two parts. Part where the r is larger than 0, fxy rxy, plus the part xy where r is less than 0. The same thing, fxy rxy. And if there's xy's, if there's edges where the r is 0, well, then they contribute nothing. We can just ignore them. So, and now we want to bound this, and we see that this is at least as large as, well, it's at least as large as when we go on the negative side, on the positive side, say, then the flow is always at least 0. And this will be a positive contribution. So it's decreasing when we make the flow 0. And here, the contribution is negative. The flow is always positive, non-negative, and the r is negative. So it's decreasing maximally if we sets the flow to the capacity. So this is at least as large as pi of t times f plus the sum over the xy with r is less than 0 fxy rxy. But now we come to the crucial observations. When if f satisfies the optimality criteria, then if rxy is greater than 0, then this means that the flow is 0. And if rxy is less than 0, then this means that the flow is equal to the capacity of the edge. And this shows that in this going from here to here, in both sides we have equality. Here we have this equality. And so the flow, the cost of the flow attains a lower bound on the cost of the flow. So it's a min cost flow. F is min cost. Yeah, so this is the optimality criterion with its proof. And now we are going to approach our goal. Here is this description of the algorithm. So we are going to maintain a pair of a flow and potential which is optimal by this criterion. And so you initialize with zero flow and the zero potential and so the potential difference is always 0. We can be in this position, but then the flow is 0, so it's fine. It's an it's optimal pair. And now let's assume we have a f and a pi, flow and a potential, and we want to go further. So to do so, we define an auxiliary network in star. So it depends on the flow and the potentials. The vertices, well, we just take the vertices of our original network, and the edges, we put an edge xy into this network, if and only if so case 1 is that this is an edge in the original network, and we have phi of y minus phi of x is equal to the cos of this edge. And we have that the flow is below the capacity of the edge. So in this case, we still have capacity for flow in the direction of x to y. And the other case is that we include a backward edge, that we have an edge which already carries some flow, and we can return something. So we have the same condition here, that we are at the cost, but this time we require that there is a positive flow in this edge. So this is the edges in the auxiliary network, and now our algorithm that we design has two steps. It has a flow increasing step, so let's call it inc_f, and this is depending on the existence of an S to T path in this auxiliary network. And what happens here is that we increase the flow, we add 1 unit of flow on this path. Add 1 unit of flow to this path. Yeah, so this is a flow increasing step, and then we also have the potential increasing step. And now this is based on the condition that there is no path from S to T. S to T path in star. Now in this case we define a set I. So this is the set of vertices with the property that there is no S to Y path in the auxiliary network. This is non-empty because P belongs to this set. And what we do now is increase the potential pi by 1 on the elements of I. And, well, in both cases, after doing this step, we update and start. Of course, by adding flow or changing the potential, the conditions for being in the auxiliary network change, and we have to update. Yeah, and now the claim is that these steps, let's make it a lemma, these steps preserve the validity of the optimality criterion for the pair f phi that we carry through. Now, in the case of inc_f, this is only changes f on edges with pi of y minus pi of x equals the cost. And they are not restricted by the optimality criteria. So after the change of f, the edges where the criteria have something to say are still valid. Now, I think P is a bit more involved. So we distinguish three cases. We look at an edge with the property that the cost of AXY is less than 0 before this step. Now, actually, I'm not talking about 0 here. I'm talking about pi y minus pi x. Now, by the optimality criteria, we are in this case, and we have fxy equal to cxy. And after this step, we have changed one of these values by 1. And the a is an integer. So now we are in the less equal case. And the edge is 5. Either we have a condition and the condition is fulfilled, or we are in the equality case and we have no condition. And now the second case, if the cost is larger than this difference, then we have completely symmetric. Before we have f of xy is equal to 0, and after we have a greater equal and are still fine. So the interesting case is the case where we have equality here. We have no condition beforehand, but we have a condition after it. So if AXY equals pi y minus pi x, now in this case, we distinguish two subcases. So the first one is if x is not in I, but y is in I. So we can reach x from S in the auxiliary network, but we cannot reach y. So this clearly says that the edge x, y is not in the edge set of the auxiliary network. And now, because we have this condition, and we are talking about an x directed edge, and we, from the definition of the of the network, I guess we still have it up there. We see from the definition of the network? No. From the definition of the auxiliary network here, this one is the one we need to look at. We see that we have no capacity left. So we are already at the capacity. But now, what happens? We are after pi increment. We have increased this value, and this value is kept the same. So we have that the cost is less than this difference, and we are fine. And now the other case is that the x is not reachable, but the y is reachable. Y is reachable, y is not in I. Now, in this case, we can clearly say that this is not in the edge set of n star. And to have this, we know that f x y is equal to 0. Otherwise, we would put this edge in the auxiliary network. And now, what we get here, we are decreasing the right-hand side, keeping the left-hand side. So after the pi increase, we have a greater, and the flow value is on the right side to satisfy the optimality criterion. So we are fine. Yeah, so that's it. We have seen that both the increment f step and the increment p step preserve the optimality criteria. And now the next thing we have here is a small lemma which talks about the very specific networks that we have related to our poset. So we call it lemma A because it's related to the cost. If we have a network which comes from poset P, then it holds that the pi of y double prime minus pi of x prime is at most the cost of the edge for all edges x prime, y double prime in the network. F pi satisfies or obtained by the algorithm. This is a statement. We run the algorithm, and throughout we have this invariant. Yeah, and where does it come from? Well, suppose not. Then we can say there is a moment during the execution of the algorithm, where this difference on the left side equals the cost. And now after the step, we have a greater. So what we do is we increase the potential of y double prime, and we keep it as it is on x prime. So we have y double prime is in I, and x prime is not in I. Now we use a special property of our network. The capacities are 1. So the only values that a flow can have on the edge is 0 or 1. And we are going to look at the two cases separately. So if f of x prime or double prime is equal to 0, then the conditions are so that this is a guy in our auxiliary network. And still we have but so this is in the auxiliary network. We can increase the flow, but now if x prime not in I implies x prime reachable, implies, since these edges in the auxiliary network, this is reachable. And this is a contradiction because we're assuming that y double prime is in I. And the other case is very similar. If f of x prime y double prime is equal to 1, well, in this case, we see that necessarily the flow which is carried from x prime to y double prime has to come from somewhere, and the only in edge of x prime is the edge coming from S. So this edge has to carry flow. So f of S and x prime is equal 1, and then we see that that S x prime is not an edge of the auxiliary network. The S to x prime path has to arrive at x prime via back edge, backwards edge. But now the only backwards edge which is a candidate here is this must be y double prime x prime in E of n star. And now we see that x prime not in I implies y double prime reachable. and we get the same contradiction that we had before. Because the path from S to X prime that exists in the auxiliary network has to go via Y double prime. Good. And now we can carry on, and the next thing that we are going to do is we are going to take the flow of the algorithm, and from this we are going to extract chain families and anti-chain families which are orthogonal. So from the flow we are going to get a chain family, and from the potential we are going to get an anti-chain family. And as I said, the two are orthogonal. And from these orthogonal pairs, we will see that we readily get all these structures that are claimed in the 5 theorems. What else? Let's keep maybe this one is. So what we do now, we from the pair F pi flow potential to a pair C A. And of course we assume that this pair is a pair that we arrive at in the execution of the algorithm. So it's, from what we already saw, this is Minkow's flow, and this is the corresponding potential, so that the optimality criteria are satisfied. Okay, now let's assume that the flow value is n minus k. So we already know that there exist flows in this network for every value between 0 and n. So this is how we can describe the flow value, and the potential at t shall be L. Okay, so what we do is we consider the set of all vertices with the property that the yellow edge in the network is carrying the flow. This is h of f, and these are the only edges which have a cost. So the total cost of the flow is equal to the size of this size of h of f. Now we look at the remaining vertices, and of course the number here is equal to n minus c of f. So we abbreviate this as C of F. And now on this set, we look at the flow, and the flow on this set is a matching in the split. So flow on XF is a matching in the split of P, and so it yields a chain partition of P restricted to XF with the number of chains is equal to the size of XF minus the number of matching edges. So the number of matching edges is equal to the total flow minus the flow that we have subtracted, that is on these yellow edges. So the number of matching edges is size of F minus cost of F is equal to the size of F is n minus k minus C of F. And the size here is equal to n minus C of F. So in total, we get k chains. So what we have seen here is that F induces a chain family CF, and the number of chains in CF is equal to K, and the number of elements covered by CF is equal to this. This is a set of elements covered by this chain partition, and so this is equal to n minus the cost. Good. Now this is the chain family, and now let's continue with the empty chain family. So we define AI to be the max of the set of all x with the property that phi of x prime is less than phi of double prime is equal to I. So because of this, taking just the maxes, we see that AI is an antichain, and A equals A1 union A2 union AL. We can go up to the total potential, which is L by definition. So this is an L antichain. And now what we want to show is So this depends on phi. So the proposition is that A, we always take the F, the C first. The F, A pi is orthogonal K. And so this implies that that the size of CF is equal to H of CF, and symmetrically the size of A pi, the number of elements covered here is equal to the corresponding width. So we get maximal families of chains and maximal families of antichains, and correspondingly saturated chain partitions and antichain partitions. Before we prove the proposition, I propose that we go back to this example and we look at an execution of our algorithm on this example and on the objects that we are going to get, just to kind of get it down to something more concrete. So executing the algorithm. So the network is still there. We are going to run it on this particular example. So S, T, A, B, C, D. At the very beginning, we have all the edges with cost 0 in our auxiliary network. So this is the n star at the beginning, and we can push flow. We can apply one. We find a path from S to T, and we can send flow. And now these three edges which carry flow are as backwards edges in our auxiliary network. Now still we can reach T, so we can again apply inc_f, and we push flow here, and now these blue edges are also reverted. And now at this point, you see from S, starting from S, you can reach C, you can reach D, and that's it. You cannot go further. This is the status. So now we have to call an instance of increase potential, and we increase the potential to 1 on these two vertices. So increasing the potential to 1 here means that now the potential here minus the potential here is my the potential difference is at the cost, and we put these edges in our auxiliary network as forward edges. And now, at this point, the number of vertices that we can reach on path from S to, sorry, this was wrong. These two are the two reachable guys, and we increase the potential on all the other guys. So we increase it on these guys. This is the new potential. So this is after the first ink P step. And now, yes, the potential of x double prime minus the potential of x prime is 1, and this curve is equal to the cost, and we add this edge. But now, if we look at what is reachable from the source, we see that still this is reachable, these are reachable, but now these two blue edges block. We can go down here, and we can go down here. So this is a set of reachable elements, and we don't reach T, so we have another ink of P step, and this time we have a 2 here, a 2 here, and a 2 here. And with this change from on these two values, we also get these two edges in the auxiliary network. And now we can actually reach T by, say, we go up here, down here, up here, up here. And there's a second path, which is up here, down here, up here, up here. And these two paths are share no edge, so we can use them, first one, then the other. So we can continue with ink F step and then ink F step. And this gives us a way of, we can look at the execution of this algorithm. And so the first step was a increase flow, second step increase flow. Now we increase potential, increase flow, and here we stop because here we are at the value n. And now with each of these points on this path, we have a chain family and we have an anti-chain family, and they form an orthogonal pair. And from this we get, if we believe to the proposition. And now, if we go here, then we increase the flow, so we change the chain family, but we keep the anti-chain family. And from this anti-chain family A, we have seen that there is a saturated family, a saturated anti-chain partition A+, and this is unchanged here. So this is a transition phenomenon. And then we get, here we keep the chain family. So we keep the C plus, which is a chain partition. So this is again, we have the same saturated chain partition for two consecutive values of L. And yeah, and then so we get all these things. We see that we have from looking at the points at different. So this is H, and here this is W. Yeah. So we and this shape is the Ferris diagram. So and it's easy to see from what we already said that this shape is actually the Ferris diagram that we need for theorem 5. In general, this shape will look more like say this, and now, of course, this is a reflected Ferris diagram, but if we do the reflection here at this line, we get a Ferris diagram in the way I have drawn it. Okay, so now we want to prove this proposition. Yeah. To show that this is an orthogonal pair, we have to show two things. So we have to show first that if we take the union of the two things, then we get all the vertices. And the second thing is that the intersection of A and C is equal to 1 for all A in A and C in C. Good. Let's start with the first one. So consider an X which is not covered by the chain partition. So by the chain family. So from the way we did this, we know that actually it should be up there. Yes. From the way we did it, we know that this means that this is a yellow edge which is a carrying flow, which means that X belongs to H of F. Now, if we have an edge which carries flow, then by the optimality criteria, we cannot be in this case. So, so pi of x double prime minus pi of x prime is less equal a of x prime x double prime. No, we cannot be in this case. Sorry. But now from the so the two values here are different. So this means that there exists an I such that X is in Mi, which we define as a set of x's with phi of x prime less than phi of x double prime equals I. So now if x is in the maxima of Mi, implies that x is in AI, and we are done. So otherwise, if x is not in AI, then there must be some other element in Mi which is dominating x. There exists a y if x is less than y. And this is in Mi. But now, if we have a comparability, then we have the corresponding edge in the network. And we have phi of y double prime minus phi of x prime is the same as because phi of x double prime is equal I and phi of y double prime is equal I, and this is equal to the very same value that we have here. And we can also put it this way. So now from the this is greater than the cost of this, and this is a contradiction to lemma A. So this cannot happen. Okay, so this proves that if we have something which is not covered by the chain family, then it's in one of the antichains. Good. Now, now we go to the second property, and for this we look at a chain XR be a chain of C. So the C is a C of F, and this is one of the chains that is given by the matching edges in the split. Yeah? And yeah, so these are matching edges. This implies that F of xi prime, xi plus 1 double prime is a matching edge, is an edge which carries flow for all I from 1 to r minus 1. Now, so let's have a look at this situation. Here we have x1, x2, up to xr. These are the x prime copies. These are the double prime copies. And what we just said is that in all these edges here, we have flow. And by the optimality criteria, we know that the potential of xi plus 1 double prime minus potential of xi prime is now at least, we have flow, so we are not in this case, so it's at least the cost of this, which is 0. So the potential differences here satisfy this inequality. But now lemma A this is equal to 0. So the difference is 0, so we know that on these blue edges the potential is invariant. And now we look at this guy, and we observe that by the construction of our matching in the, we know that there's no flow on from here to t. So f of x1 double prime t is equal to 0. And now, again, the optimality criteria tell us that the pi of t minus pi of x1 double prime is less equal the cost, which is again 0. And now the maximality of t implies, so this cannot be larger than the potential of t. In every increase of the potential of t is increased. So maximality of pi of t implies pi of x1 double prime is equal to L. And now let's look at this one here. And here we again see that the flow of S and XR prime is 0, because this is this guy is not matched in our matching in the split. And again, the optimality criteria tell us that pi of xr prime minus 0 is less equal 0, but non-negativity tells us that pi of xr prime is equal to 0. And finally, again, lemma A says that the increase of the potential on one of these vertical edges increase of potential on vertical edges is bounded by 1. Yeah. So now let's look at the potentials. We start with the 0 potential here. We end with the L potential here. And on the blue guys, the potential is the same. So for every I, we have one of these edges such that the potential here equals I, and here it equals I plus 1. So in this, on this chain, this was an arbitrary chain of our chain family. And for this arbitrary chain, we have the property that for every I, maybe I should have put I here and I minus 1 here. For every I, we find one of these guys, so that the potential here is I, the potential here is less. So this will be an element of Mi. And now, suppose that this element is not an AI, then we construct a contradiction which is very similar to this one. So yeah, so what we achieve here is that for, I repeat what I said here, for all p 1 less equal p less equal L, there exists an xi such that xi is in mi. No. Such that let's do it explicitly. That pi of xi prime is less than pi of xi double prime, which is equal to p. And this is actually equal to p minus 1, but this is not so relevant. So xi is in MP. So this is what we found from the discussion of the potential values along this zigzag corresponding to the chain. And now suppose that xi is not in AI. This is the same thing that we got there, and there exists a y in mi with, this is a p, sorry, with x is less than y. And then we have this x prime by double prime is in E of n, and we have pi of y double prime minus pi of xi prime equals 1. Because it's the same as the difference of these two values, and this is now larger than this, and this is a contradiction to lemma A. Yeah, so the very same argument that we just did on the other blackboard, and Yeah, so this shows that that this chain C that we have intersects AP in one element for all 1 less equal P less equal N. So this is, we took an arbitrary chain from the chain family and we get this intersection, and this is the second property of the orthogonal pair. So this completes the proof of the proposition. And yeah, on this board with this example, I already indicated that from this statement and from what we know about the sizes of f and pi, the flow value and the potential value, we know that we get this kind of increasing path, and for each point on the boundary of this path, for each point on this path, we get the orthogonal pair, and this allows us to derive the 5 theorems from just this one proof. And I see that I'm already quite a bit over time. Sorry for that, and that's it for today.